The artificial intelligent voice just said recording in progress. So recording in progress. All right. It's Saturday. I have no idea which day it is. Saturday, it's 4th of March. Hope you guys are having a good time at home. So this is going to be the lecture for 7th, which you're going to see on 7th. So without much introduction, let's get started. So we're going to I'm going to talk about alcohols for about an hour. I think we started around, according to the clock in my office, around 4:40. So we're going to go until roughly 5:40. So whatever we can cover about on alcohols. We have already started the chapter on alcohols. We have already started discussing alcohols, naming alcohols, stuff like that. So we're going to talk about synthesis of alcohols, a couple of routes, and then talk about some reactions of alcohols. And then that'll be it. And after an hour, there will be a quiz. So I will communicate one more time, maybe 2 more times with you guys so that no one shows up for the in-person class on Tuesday through Canvas as well as my Fresno State email. So let's get started. All right. So I think the style is going to be very similar. This is my office. This is my whiteboard. This is how I taught during pandemic using Zoom, but the Zoom was extended to everyone in the class. So most of the students didn't turn on their camera, but that was a constant gripe that I had. But some of my students did turn on the camera, and I'll once in a while have chit chats. There was apparently in Chem 8 class at some point, there was a kitten that the student told me that the kitten loved to listen to me. She would sit on the computer keypad and stare at the screen. So I guess I can be a cat whisperer. Alternate career if I get fired. All right, Kim 128B. And even though it's not going to be 7th today, but it's going to be, you guys are going to see it on 7th, which is Tuesday morning. Yeah. So we're talking about alcohols. And alcohols are essentially, you have an OH and an alkyl or cycloalkyl group. It can also be an aromatic group, but since we haven't talked about aromatic chemistry, aromatic molecules, it's too premature. It's inappropriate to talk about aromatic alcohols at this point. I think we're going to talk about it when we talk about aromatic compounds. So essentially, these guys look like this. ROH, and R can be alkyl or cycloalkyl groups for the time being. Okay, R is alkyl or cycloalkyl. I am going to write down that the third option is aromatic. They're called aryl groups, ARYL, aryl, but we won't talk about it. I'm going to put that in parentheses. Okay, let's hold off on that. Let me just talk to you guys about the 3 kinds of alcohols that you can have. Okay, so one kind of alcohol is this. Okay, I'll tell you like why they're different. The second kind of alcohol is this. The third kind of alcohol is this. Well, what's the difference? The difference is the alpha carbon format. The alpha carbon, what is the alpha carbon? This is the functional group. OH makes an alcohol, so it's kind of an important part of the molecule, right? So this is your alpha carbon. These are your beta carbons. You know what? Just focus on alpha. Okay. When you have two or more alpha hydrogens, it's called a primary alcohol. Okay. Number of alpha hydrogen greater than equal to 2, then it's called primary alcohol, 1 degree. When there is one alpha hydrogen, okay, it's called secondary alcohol. When there is none, 0, there is nothing here, okay, then it's called a tertiary alcohol. Irrespective of their nature of their alcoholism, that doesn't sound right for some reason. Depending upon their nature or format of the alpha carbon, all alcohols are nucleophiles because of this. It's got 2 lone pairs, it's a nucleophile. This guy got 2 lone pairs, it's a nucleophile. This guy got 2 lone pairs, it's also a nucleophile. They're all nucleophiles. Okay. So remember that there can be 3 different kinds of alcohols: primary, secondary, or tertiary. The other kind, which is kind of an unique kind, which is methanol. Where you have, I'm going to turn off my phone. Forgot to do that. Sorry about that. It chimed. It's got three alpha hydrogens, 1, 2, and 3. It's just a methanol. It's just methyl alcohol. There is no specific name. There is only one of that kind. But there can be many of these primaries, many secondaries, many tertiaries. Okay, and remember that all alcohols can be nucleophilic. Okay. I'm wondering, I didn't do it for my Chem 8 lecture. I'm wondering if I should take still pictures, even though the video is going to be available for you anyway. I might do that. All right, so this is just a description of alcohol. I'm tempted to talk about hydrogen bonding, but I think I would like to do that in person when you guys are there and sitting in the classroom. So I'm going to hold off on that. So let me just, for Ch128B, you guys probably deserve a little more special care. So let me just take a snapshot. It sounds weird, but then let's do it. I'll post it as 3/7/23 still photos. All right. There's not a whole lot going on here, so I'm just going to erase it. Okay, then comes the synthesis. We talked about the synthesis. Before we talk about the synthesis, let me just tell you one important aspect about alcohols. Again, it would be very appropriate to talk about hydrogen bonding right now, but I'm resisting my temptation right now. So when you have an alcohol, whatever alcohol it is, Unlike alkanes or alkenes or alkynes or other boring nonpolar compounds, the the electronegativity of oxygen is 3.5. This is 2.5. So the difference between their electronegativity is 1.4. 1.4 is a big number, especially when we're talking about the span of electronegativity is like point something to 4. Fluorine has the highest electronegativity. In a scale of point something to 4, 1.4 is a pretty huge number. So this bond is pulled toward oxygen, and therefore this bond is highly polarized. Delta minus here and delta plus here. Small charge here and small charge here, right? So what's the bottom line? The OH bond is a very polar covalent bond. Polar covalent bond, and therefore it depends. You guys have done some experiments in 129A, and if you have taken 129B, you may have seen more of alcohols. I'm not sure exactly what is taught in 129B. For quite some time I have not taught it, but then the bottom line is, I think there was an experiment when you start increasing the alkyl chain of the alcohol, you start increasing the size. Methanol, ethanol, propanol, pentanol, hexanol, as the length of the alkyl part increases, even though methanol and ethanol were water soluble because of this guy, the OH part, this is like water. The OH part, the hydroxy group, is like water, not it likes water. That's not what I'm saying. It is kind of like the water molecule, right? And therefore, just for the sake of it, if you have forgotten or if you've never heard it from me in the past, they do hydrogen bonding. We can discuss it on Thursday, first thing on Thursday morning, Thursday at 12:30. Okay, so they like each other, and therefore an alcohol is expected to be soluble in water. Okay, but realize methanol, small baggage, small alkyl part. Ethanol, little bigger alkyl group. Alkyl group is greasy. Remember that. This part is polar. This part is polar. The alkyl part is not polar. Non-polar. Okay? But methanol only has 1 carbon, 3 hydrogens. Ethanol has 2 carbons and 5 hydrogens. So the alkyl baggage is not that big. It's only a carry-on luggage, or like a little handbag, or my van purse. Okay, small. So these two guys are water soluble. As the size increases, as the alkyl group starts to increase, solubility of the alcohol in water becomes a problem. Okay, so for example, if I skip a few of them, 2, 3, 4, 5, 6, 7, 8. This guy, octanol, can be a problem. What's going to be the name of this molecule? 1-octanol, because it's on carbon number 1. You might say, you might argue that, oh, it has a hydroxy group, it should be water soluble, but well, look at the length of the non-water loving part. This side does not like water. Does not like water. this part likes water. So most likely you can do an experiment. Actually, I think this was an experiment in 129A. As the size increases, are they miscible? Is the alcohol miscible with water? This is not. This guy is insoluble in water. Okay, just like a little, information fact about alcohol's properties. All right, so that's that. What else can we talk about it? When I talked about substitution reactions in the previous semester in fall of 2022, I used to write a list of different nucleophiles. Those of you who have taken this course from me, you will probably remember that on the right side of the board in blue, generally in blue color, I would write a list, start with water, then sodium hydroxide, then different alcohols, then alkoxides. Alcohol minus the hydrogen, and I used to say that those are really awesome nucleophiles. They're better nucleophiles than a regular alcohol. Regular alcohol is an okay nucleophile, just like water. But if you could pull the hydrogen out, like sodium hydroxide, OH minus, if you could remove the hydrogen and make it O minus, obviously that would become a much stronger nucleophile. So how can you do that? So this is going to be the first reaction I'm going to show today for alcohol reaction, since we are kind of still having a general talk. Okay, so if you take an alcohol, I'll follow the same color coding. If you take an alcohol, and if you think that it's not going to be a strong enough nucleophile, you want to make that a better nucleophile, you can actually do that. You can pull out the hydrogen using a very strong base, something that's got a pretty strong, powerful negative charge. And that something can be different species. It can be, I'm going to give it to you. I'm just going to tell you, okay. Sodium hydride, okay. Sodium hydride is, you guys can figure it out and tell me whether the sodium hydrogen bond is actually a polar covalent bond, non-polar covalent bond, or an ionic bond. Figure it out on your own. That will help you relate to this molecule. Sodium hydride, depending upon their electronegativity values, I might sneeze. I'm having serious allergy problems. If I sneeze, I'm asking for advanced apology, forgiveness. Okay, sodium hydride, which way the electrons are pulled, toward hydrogen or toward nitrogen, toward sodium, figure it out. Okay, so one reagent is this. If you take sodium hydride, what will happen is you will make this molecule, the incredibly awesome nucleophile. And let's say the hydrogen's electron is a blue dot, Blaupunkt. That used to be the name of an audio system from Germany. Blaupunkt means blue dot. I just happen to know. Okay. Oh, what happened to the hydrogen? Let's not talk about it. So you get RO minus and sodium plus as a cation. Okay, this is kind of encroaching. Separate discussion. Okay, so RO minus and sodium plus. So you can always make a more incredibly awesome nucleophile from an alcohol by doing this, unless the alcohol has some other part, vulnerable body parts that can get messed up with sodium or sodium hydride. you have to like figure things out ahead of time. You have to plan properly. This guy is called, this is an alcohol. This is called an alkoxide. Hey, it's not C. Now I'm having second thoughts. I think alkoxide is ALKOXIDE. You guys can figure out and shoot me an email like, Shantanu, you're wrong. Okay. This is an alkoxide. So alkoxides are better nucleophiles. All right. What other ways you can get this job done? You can also use just sodium. Don't do it because it can be pretty dangerous. So sodium hydride, or not all of them together. Sodium hydride or sodium, or ready? Potassium. Not a good idea. It has to be done in a very controlled manner. Either of the three reagents, if I were you and doing this chemistry in our lab, this would be my choice. Least dangerous, least smallest chance of things catching fire in the hood. Sodium hydride or sodium or potassium will make you an incredibly awesome nucleophile that's going to be RO minus. Okay. Small board, so the number of pictures will be more. If you take a second snapshot. Who is writing? Oh no, okay. Okay. All right, that's what we discussed. Solubility, some property of an alcohol. Alcohols love to go in water, but you have to be careful about your judgment, because if the alkyl part is too big, it may not be very soluble. Okay, it might make two layers. It'll still like to interact with water, but it may not be totally soluble. All right, let's erase. Let's keep moving. So that's that. And then we talked about reactions of, well, we talked about the synthesis of alcohols. We have already seen two different synthetic methodologies in 128A, okay? And I expect you to kind of know that. As I said, I'm not going to go through the details. If you have any questions, if you want me to go over that, come see me during office hours. If you come with some other friends, preferably from our own class, I will appreciate it more. And you can always go and talk to Erisa, essay leader. Okay. I am going to erase this also because I might need this space. My board is not as large as in the lecture hall. Okay, so synthesis of alcohols. Synthesis of alcohols. It's 5:04. When did we start? Does it talk about it somewhere? Recording. Okay. I think we started around 4:40. Okay. So synthesis of alcohols. We will talk about a couple of methods that we have already seen. Okay. Let's say we have an alkene, unsymmetrical alkene. Unsymmetrical alkene, I'll just show you something important here. It's an unsymmetrical alkene because it's got one type of structure on one end of the double bond and another type of structure on the other end of the double bond. It has different number of hydrogens at the ends. Okay. On the right side, okay. On the right side, it has two hydrogens. Realize that hydrogen is small. Hydrogen small. An alkyl group, methyl, ethyl, propyl, whatever, cycloalkyl, an alkyl group, alkyl or cycloalkyl, is big. Okay? More hydrogens you have, less substituted it is. Think about it for a second. Close your eyes and think about it. More hydrogens, less substituted. You need to do it while you're meditating. Less hydrogen, more alkyl or cycloalkyl groups, more substituted. Think about the word substitution with branching. So if I ask you the two ends of the double bond, the right end is carbon 1, left end is carbon 2. Which side is more branched, more substituted? That side. This is more branched. This is less branched, less substituted. Think about hydrogen like a little leaf. Think about hydrogen like a small little leaf. And think about the alkyl groups like a real branch. Okay? The alkyl groups are real branch. Where is my brown pen? These are real branches. This is a branch. This is a small branch. This is a branch that has a branch. Okay? And this is a tiny branch. It's not a branch. It's just a leaf. That's a hydrogen. That's a methyl group. That's a propyl group. That's a sec-butyl group. Whatever. Okay? So those are branches. More branches, more branched, more substituted. Get that in your system. All right. So this is silly talk. Okay. I'm going to make this guy a little smaller up here. I need that space. I just can't use, we don't have that luxury of that lecture hall. 1, 2, 3. Okay. I'm just going to use the molecule in one color. Propene. If you take propene, I'll use the reagents in different colors. So let's do the first reaction in blue. H plus, H2O. Acid catalyzed hydration of an alkene. Acid catalyzed hydration, adding water, of an alkene, double bonded compound. Okay, it goes through two carbocations, more stable and less stable. Tertiary carbocation is more stable than secondary, than primary, than methyl. We talked about it in 128A. If you're not there, come and see me. So the more stable carbocation will produce the major compound, major product. Less stable carbocation will produce the minor compound. Let me just do it this way. Just draw one line. H plus and water will get you this guy. One product with the alcohol in the middle, one product with the alcohol at the end. If you're still having trouble visualizing it or making sense out of it, you need to study. You need to study to seek help. SI leader, me, fellow students, somebody else. I don't care if you go to somebody else, if you're more comfortable with any other organic professor. I don't have any such problem. I mean, I don't know about my other colleagues, but then if you go for whatever reason, just get help and get up to speed. I don't want to see, I want to see a happy ending. That's my personality. I like happy people, happy ending, good scores, good grades. I don't like to give bad grades to anybody. This is major. That's a terrible looking major. This is major. This is minor. It goes to carbocation, and this is Markov-Nikov product. This is anti-Markov-Nikov product. Okay. There is another procedure that also gives you the major product pretty much exclusively, and it's a pretty nasty reagent. Okay, the nasty reagent that gets you here is the following. I'm not sure if I talked about it in alkenes when last semester. I may or may not have done that. Okay, it's called oxymercuration. I think I mentioned it, but I don't think I showed the mechanism. It's called oxymercuration. What's the reagent? Really toxic reagent. Mercuric acetate, step 1, AgOSC, it's acetate. I will explain at some point, not today. And water. And in the second step, you use sodium borohydride. It's a reducing agent. Just for the sake of understanding right now, it's a reducing agent. We talked about it in SN1, SN2. If just think about sodium borohydride as a source of hydride, H minus. This is a hydride, HYDRIDE, not proton, but hydride. So sodium borohydride produces H minus. It's a reducing agent. It adds H minus to wherever it can dump it. Okay. If you do oxymercuration reaction, you also get the major product. And there is something special about it. I'm not sure if I'm going to talk about it today, but maybe some other day. If I can pick up some speed, hopefully. Some of you are probably wondering, like, yeah, it's not going to happen. But then if I can pick up some speed, maybe we'll discuss it at the end of the semester. Okay, so acid catalyzed hydration gets you the Markov-Nikov product. Oxymercuration, mercuric acid and sodium borohydride gets you the Markov-Nikov product. Oxymercuration does not produce carbocation. If someone has told you oxymercuration goes to carbocation, he or she is wrong. Oxymercuration does not produce carbocation, period. That's it. What if you want the minor product? What if you don't want this guy? What if you want the minor product? What if you want to make 1 propanol, not 2 propanol? Well, there is a way to do that. It's called hydroboration. What's the cocktail? What's the recipe? Borane, BH3. First step, that's it. And a solvent. Borane sometimes comes with a solvent. Borane ether, borane THF complex. Not today. Step 2. We have discussed it in 128A. Water, a cocktail of 3 different things. Water, sodium hydroxide, and hydrogen peroxide. What do you accomplish? Well, you make the minor product exclusively, nothing else. Anti-Markov-Nikov product. And that's it, nothing else. Not a single drop of, not a single molecule of the Markov-Nikov product, only the other molecule. Okay? This methodology also, no carbocation, no production of carbocation. I don't think the book ever says that, but the book sometimes says, or people have, I know some of my colleagues have said, oxymercuration undergoes carbocation. It doesn't undergo carbocation. It forms like a triangular carbocation-like thing with the mercury. Okay. Later on. So if you see an unsymmetric double bond down the road in the future, in quiz 2 or test 1, quiz 2 or test 2. Quiz 2 or test 2. If you see something like an unsymmetric double bond, and if I'm asking you, how do you produce this alcohol or this alcohol, you should keep in mind that you do have opportunities, you do have the options, you do have the knowledge and ammunition to make it happen. You know the recipes for making whatever different products. You have to use a different recipe for making a different product. Okay, so let me take a snapshot of the board. And I'll keep going. I'll let you stare at the board for a second. Okay. This is something that we have actually discussed in the last class. Okay. So we can take an alkene and make an alcohol out of it. So that's procedure 1, synthesis of alcohols. Let's go for another procedure. This is old stuff. Chemistry that you have learned in the first part of organic chemistry. Second part of organic chemistry, you have learned, too many pens. I'm dropping the brown pen. All right, second part of the synthesis, synthesis number 2. Another procedure is, you have seen, nucleophilic substitution reactions. Take a alkyl halide, hit it with water or sodium hydroxide, a better nucleophile, you get an alcohol, right? SN1 or SN2. It's very well known. So what you do are X is a living group, and usually it's a halide. X is equal to fluorine or chlorine or bromine or iodine. You must have had a strong dose of it, whether it was me or anybody else. And then you hit it with a nucleophile. Whatever nucleophile, I'm not going to draw the list of nucleophiles, and you basically swap. The leaving group leaves and the nucleophile gets in. Okay. It's not funny. I know the person who thought it was funny. Okay, R nucleophile plus halide minus X minus. This is like the generic version, right? SN2, 1 step, boom, boom. It comes from the backside, it goes out, and it produces that. SN1, Detachment happens first because it loves to make a carbocation. Tertiary carbocation is more likely, etc., etc. You know, SN2 goes for primary, and then you can mess with the solvents. You can kind of like use solvents of your choice to make the reaction go in your own way if it is secondary. So an example is, well, how about alkyl 1-chloroethane, and you hit it with sodium hydroxide. An awesome nucleophile. Water might work, but it'll be a sluggish reaction. And this reaction is going to be two-step because it's not two-step. One step, bimolecular. It's going to be SN2 because primary alkyl halide. Can you change the course of the reaction by using a solvent? Can you mess with the solvent? Even if you use a polar protic solvent, it'll still go SN1, SN2 because it's primary, it's born primary, it can't make a carbocation. Okay. So it'll form our favorite alcohol. No, this is not our favorite alcohol. Don't drink propanol. Oops. This is 1 propanol, not 2 propanol. Okay. That's what happens. So you can use SN1 or SN2 to make alcohols, whatever, right? Another example, this is going to be SN2. And if you take this dude, the chicken foot chloride, or let's use something different. We have never used iodine because it's expensive. Come on, we can afford it. Let's use iodine today. Okay, how would you name it? Figure it out. I'm not going to tell you. And this reaction, let's use water. Let's just use water. H2O. Let it be a sluggish reaction. Who cares? We'll just set it up and go home and come back on Monday. And it's going to be two-step reaction. And it's going to make the chicken foot alcohol. Tert butanol. So that's the nickname. Okay. SN1. It's the SN1 cloud. Okay, so two reactions, SN1 and SN2, they can produce alcohols as well. All the regular rules and regulations apply to how to maneuver, you know, the mechanism, like how it exactly happens. I'm not going to get into the details. So this is procedure number 2, how to make an alcohol. All right, take a picture. I think I should just start doing online teaching. That way I can go faster. Because when I don't see the person, I'm less likely to talk too much. I still talk, but not probably too much. But I'm already talking too much. Or chemistry, substitution reactions. All right. Reactions of alcohols. Let's get started. Before we get started, 524. Okay, we have some time. Another reaction that I am not going to show you how to make an alcohol is kind of a reverse way of going. I'll tell you like what I'm talking about. So you can actually reduce a carbonyl compound, but I want to discuss synthesis of alcohols from carbonyl compound when we talk about carbonyl compounds, not now. I'll just show you how this reaction might look like. It's still under synthesis, okay? If you take an aldehyde or a ketone, another synthesis by reduction of carbonyl compounds to be discussed in details later. Okay, not right now. I'll just show you like what happens. If you take a carbonyl compound and I don't know, an R group here, R1 here, and R2 here. Okay, R1 is alkyl. R1 is alkyl or cycloalkyl or aryl. I'll put it in parentheses because we haven't talked about aromatic compounds yet. Aryl. Okay. When you think about aryl, if you really want to know what I'm talking about, think benzene. That's an aromatic compound. Benzene is an aromatic compound. Hexagon, cyclohexane with 3 double bonds. Okay. When you do that, and R2 has to be different for aldehyde and different for ketone. Okay, we are talking about aldehyde or ketone. So R2 will be when R2 is hydrogen, the compound is an aldehyde. When R2 is not hydrogen, is one of these guys, alkyl, cycloalkyl, or different color, something new. Aryl, aromatic. When it's one of these, then the molecule with carbon and carbon connected to the carbonyl is called a ketone. We will discuss them in details later. If you take this guy and react it with what you have seen before, if you take this molecule and you react it with sodium borohydride, which is nothing but H minus, step 1, step 2, you can figure out how the reaction actually happens. Step 2, H plus water. If you pay attention to the color coding of the final product, you can totally figure out exactly how this reaction takes place. You can figure it out. It's very easy. That could be a bonus question in test 2. All right. Not too much talking, just a little bit of talking. R1 stays, R2 stays. Pay attention. Oops, what am I doing? I must be losing my mind. Pay attention to the colors, man. Green. Green. Purple. Purple. Figure out how this reaction happens. I wish I could give you guys a colored exam and I can ask you, like, figure out the mechanism. Show me the arrows and show me like how this happens. I might do that for the next quiz. That'll be kind of fun. Okay, so what is this? This is an alcohol. It's an alcohol. So from a carbonyl compound, you can make an alcohol. I'm not going to give you the details of the different reagents, the mechanism, blah, 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 blah. But the bottom line is from aldehydes and ketones, you can make by reduction, we can make alcohols. That's exactly what one of our group members did that in our research project. He actually came up with that idea. I was kind of oblivious. All right, time to take a picture. Oh, 5:30. Yes, take a picture. I have to cover the whole board. Yeah. All right, let's go forward. So now, this was the third way to make an alcohol. Okay. Remember this discussion when we talk about carbonyl compounds. This discussion will come very handy. It's kind of a preparation for you guys to get into the carbonyl discussion. Not soon, probably late April. All right, what's next? Reactions of alcohol. Hangover, unexplained happiness, unexplained sadness, confusion. Reactions of alcohols. I'm thinking in 10 minutes, let's talk about something that I'm not going to show the mechanism. That'll be easier for me to do. And then Thursday, we can definitely wrap up alcohol, and I'll probably jump to the next discussions. Wishful thinking, but then we'll try. Reactions of alcohol. Let's take an alcohol. Let's take a primary alcohol. So I'm going to split the board. Split the board in two halves. The left side is for primary alcohol, and the right side is for secondary alcohol. Okay. Ethanol. Okay. Not straight. A little better? Not better, but you know what? Let's live with it. Ethanol. Isopropanol. Secondary alcohol. It's got a hydrogen here. Okay. It's got two hydrogens here. Under reactions, first reaction that I'm going to talk about is oxidation. Pretty powerful reaction. Many oxidants can catch fire. You have to be very careful if you're ever doing an oxidation reaction in the teaching lab or in your research lab. Teaching lab, I don't think we have any oxidation going on unless there is a special project in 129B. In the research lab, if you're doing reactions with KMNO4, potassium permanganate, or potassium dichromate, can be dangerous. All right, so oxidation. First reaction that I'm going to use is called Jones reagent, J-O-N-E''S. Okay. Jones reagent, and it's chromium trioxide. It's an inorganic compound. Chromium trioxide is a strong oxidant. Chromium trioxide is present also in, chromium is present in many other species, such as potassium dichromate. You have heard about that. So chromium trioxide, when you use Jones reagent here, chromium trioxide plus sulfuric acid, H2SO4, what it does, oxidation means adding oxygen or removal of hydrogens. Gens, not one hydrogen, two hydrogens. Which hydrogens do you remove when you're doing an oxidation? You remove this hydrogen that's attached to the oxygen, and you remove one of the alpha hydrogens. Okay, you remove that guy and this guy. Over here, you remove this guy and this guy. Okay, I used to show the mechanism of Jones reagents reaction mechanism, but then for the past, I don't know, 5, 6, 10, 7, 8, 9 years, I haven't been showing it. Toward the end, again, if we have like 2 extra classes, which is unlikely, but if it happens, actually we don't really have, none of our classes fall on holidays, so we might get lucky toward the end. I will show you some interesting reactions. So those hydrogens disappear essentially in this process. Okay, on the right side, the product that you form is, this is basically minus hydrogen. Oxidation minus hydrogen. This is also minus hydrogen. Okay, so when you do the minus hydrogen, what do you get? You made nail polish remover. You took rubbing alcohol, oxidized it, you got nail polish remover. Both are useful. This is acetone, it's a ketone. So from a secondary alcohol, you got a ketone. What about here? Well, let's see. This is an aldehyde. From a primary alcohol, you got an aldehyde. Unfortunately, this story has a sad ending. If you wanted the aldehyde, you're not going to get it. You're going to get something that's over oxidized, because this cocktail, chromium oxide and sulfuric acid, is extremely powerful. It cannot stop here. Okay, can't stop. Unfortunately, it takes it to the next molecule, which is over oxidized. In this oxidation, it's not removal of hydrogens, it's adding one more oxygen. Okay, and then look what happened. This is this carbonyl, and another oxygen has gone in with a hydrogen or without the hydrogen. So you got an acid. This is a carboxylic acid. Unfortunately, in some oxidation chemistry, you can't stop it. It just goes all the way to the over-oxidized, doubly oxidized product. Almost time. So, but over here, that option is not there. For a secondary alcohol, you just cannot over-oxidize. That guy doesn't over-oxidize. You always stop at the ketone. Okay. What other reagents you can use? Well, there is another reagent called, I'm going to stop right now. So this presentation is going to stop here. We're going to start discussing oxidation reactions on Thursday again. This video we will watch after you're done. Pop quiz is going to pop up on Canvas as an assignment, under assignment, and those points in some form, like half of it or quarter of it or something, will be added to your test 2 whenever that happens as bonus points. So I'm going to write it down as test 2 bonus pop quiz. Take it online, just answer some simple questions. There might be some structures, there might not be some structures. Okay, based on what we discussed right now. I'm going to stop the video. I'm going to stop recording the video. I'll see you guys Thursday. In-person class on Thursday. Take care. Have a good day. Have a good Tuesday and have a good Wednesday.